Example M7.1, draw the shear force and bending moment diagrams for the simply supported beam shown. Okay, so first on the list, before we start to draw the shear force and bending moment diagrams, we have to determine the reactions at A and C of this simply supported beam. Alright, so to determine the reaction forces at the pin A and roller C, we have to draw out the free body diagram. Okay, but since the beam loading is symmetrical, it would follow that the reaction here and the reaction here would be equal to rather. Okay, and so if that's equal, then by summation of forces, okay, by summation of forces in the y direction equals 0, since this is supposed to be in equilibrium, then RA plus RC minus P is equal to 0. But then RA is equal to RC, right? Which is just equal to R. So 2R minus P is equal to minus P equals 0. And therefore, R is equal to P over 2, which is what we see here. Okay? So that should not be difficult for you to understand at this point in time in our study of mechanics of deformable bodies. In fact, this is an application only of statics. Okay, so since no applied loads act in the x direction, the horizontal force at the pin support A is 0, because there is supposed to be a horizontal reaction here as well. Okay, there is no other load acting there, therefore there is no reaction force there. Okay, you can think of it as, since it's not moving here, then there is no need for there to be resistance at point A, and therefore there is no reaction load at point A. Alright, so next, after that, we can begin to draw out our shear and moment functions by passing through the method of sections at this point and at this point. Again, at this point A and at this point B. Why here and why here? Why can we not just make only one shear function and the moment function? Again, because when you expose the beam at this section, the force P is still not included, right? So it changes the value of the shear at this point. All right, so the only thing, or the only force that is accounted for when we talk about shear at section A is the reaction force at A. While when we talk about the shear at the section B, then we have to include force P. And therefore, the shear force at A and the shear force at B are not one and the same. Okay? They are not one and the same. And therefore, they have different shear and moment functions. Alright? Which explains why here in this free body diagram, we have for segment AB and segment BC. Alright? So, for segment AB, we pass a section AA through the length of AB, and then we sum up vertical forces at that in this segment right here. Okay, so we have positive P over 2 minus V. Alright, so you always account for the internal shear load, where this is going down because we are assuming the shear to be positive at that point. Okay, again, I'll go back to the rules as to why that is so. Alright, okay, so anyway, so we have V equals P over 2. So the shear, or the shear function along the segment AB is equal to P over 2. And the moment function, okay, by summing up moments about section AA and applying equilibrium condition, we find that the moment is equal to negative P over 2 times X. Alright? Actually, this is supposed to be positive. Yeah, this is supposed to be positive. Okay. So, yeah, my mistake. Here it's negative, positive. So you transfer that. That's supposed to be positive. All right, then moving on. That means since we have the shear function and the moment function, we can then draw out the shear diagram only for segment AB and the moment diagram as well. All right, so here we have P over 2, so that's positive, and that means from here to here, that is P over 2. Maybe I will change the color. Okay, make that 2. Okay, so we have P over 2 here. P over 2, and that's constant from here to here. Maybe I'll just use this line function here. Okay, so that is, I change this to red, P over 2. All right, so from A to B. Also here, that is positive P over 2 times X, meaning that it is linear. So it increases as X increases, and therefore this is supposed to be a line from 0, okay, because we start at X equals 0, okay, until X equals L over 2, okay. So it's from here all the way up to there. All right, and the value at that point is P over 2 times X. X is L over 2 at that point. Okay, so this is P over 2 times L over 2, and therefore this is PL over 4. Okay, so next, for segment BC. Now, take note that we are already taking into consideration the force P. All right, so summing up forces for the shear function, summing up vertical forces for the shear function, we have P over 2 minus P minus V is equal to 0, and therefore P over 2, rather V is negative P over 2. Next, we have the moment function. So we will sum up forces about this point here, and we have negative P over 2x plus m equals 0. Actually, I think this is lacking. Let's do this manually. So we have P over 2, all right? So this is negative times x, okay, because this creates a counterclockwise moment, contrary to this, a clockwise moment rather, contrary to the counterclockwise moment where we take it as a positive. And then we have plus P, okay, times x minus L over 2, all right, and then plus m equals 0. Okay, so here we have P over 2 times x plus P times x minus PL over 2 plus m equals 0. So if I transfer everything there, I have m equals this will turn out to be positive. So this is negative P over 2 x, right? Because this becomes positive P over 2, you transfer to the other side. That is negative P over 2x plus PL over 2. Okay, so then you can draw out the shear function at BC. Okay, shear function for segment BC and the moment function for segment BC as well. Okay, so here we have negative P over 2. So here this is negative P over 2. We see that there is a discontinuity. Okay. And then, okay. And then at this point, it goes up. It's supposed to close. Alright. So, this is negative P. Okay. This is negative. Let's do that one more time. Okay. Negative P over 2. Okay. So, next, for the moment diagram, we have negative P over 2x plus PL over 2. Okay. So, at this point, okay, there's a discontinuity. So, at this point here, we will check if the value is still the same at PL over 4. Alright, so since the function is negative P over 2 times x, and we have negative P over 2 times L over 2, okay, plus P L over 2, then that brings us to negative PL over 4, okay, plus PL over 2, right? If you add that, then you will come out with PL over 4, and therefore the point remains here even on the segment BC. Okay, so when since this is also linear, okay, this is also linear, it would follow that most likely the function would follow this shape. Okay, it's descending since it has a, okay, if you think about it, this right here, okay, see, if this is a line, this right here, this is your slope. Okay, and since it is negative, that means that the slope is going downwards, and therefore the slope is going downwards here. Okay, so here we have successfully drawn out the shear and moment diagram for the given beam. Okay, and so we determine the maximum positive shear to be P over 2, and the maximum positive moment to be PL over 4. Okay, that is what we see here. Okay, maximum internal shear force is positive negative P over 2, and the maximum internal bending moment is PL over 4, which occurs at x equals L over 2. Alright, so we notice that the concentrated load causes a discontinuity at its point of application. In other words, the shear force moment diagram, the shear force diagram rather, jumps by an amount equal to the magnitude of the concentrated load. Okay, so where there is a load, the concentrated load will create a discontinuity that is equal, okay, that is equal here. If you add this up, it's equal to P. Okay, it's equal to the magnitude of the concentrated load. All right, so and here we have a better representation of the shear force and the bending moment diagram. Okay, so it's all the same here, except that there is a lot of clutter here just because I wanted to prove a point. But in any case, okay, you should present your shear and bending moment diagrams as neatly as possible. All right. So in the next video, we'll be talking about example M7V2.